Hello and welcome to the Mach-23 Critical Design Review, the INROS team from the University of Nottingham. We will first cover a high-level overview of the launch vehicle. So just a quick reminder of our mission. We are launching to 3 kilometers and deploying a CANSAT. Our mission on solar power is investigating the feasibility of putting solar panels on the outside of the airframe to keep the vehicle charged on the pad. And our mission on sustainability is investigating using fixed flaps for payload descent control. The design for Mach-23 is now frozen as the upper motor ordered, the L645 75mm free grain. This has led to a 99.6mm diameter, roughly a 4-inch airframe that's 1.9 meters tall. You can see a drawing here on the right highlighting the high-level features. This is the same as the PDR, split into 3 sections, the motor bay, the avionics bay, and the payload bay from left to right. We will be able to deploy a 2U CANSAT in length that's 75mm in diameter. The nose cone will deploy at apogee, with the drogue CANSAT being deployed. Then the main will deploy at 200 meters, splitting the airframe between the motor bay and the avionics bay. The changes since PDR are relatively minimal. The only major change is the removal of the drag reduction system. However, we will still be including the latching system mentioned to test for future use. Additionally, dedicated parachutes have been included for the payload. There were a few minor iterative changes, including slight airframe length changes, fin design iteration, and a motor change due to stocking availability, but generally nothing that will affect the budget or timeline majorly. Additionally, there's now a separate motor bay being produced from the UROC, while everything else remains the same. Parts have begun arriving, including recovery systems, though some have been lost in customs, and an airframe test piece is arrived from Collins for some compression and RF tests. So we'll now go through the design in greater detail. To aid in understanding, we will go through the design features roughly in the order they will be relevant to the mission.
The rocket baseline configuration has been optimized and iterated to meet general as well as competition-specific functional requirements from 2 different launch competitions to enter this year's editions of Mach-23 in the UK and Europe launch competition. And for this reason, most constraining environments and limiting load cases from both missions have been accounted for in the design, however, without compromising safety or performance in either of them. And this has primarily been achieved by creating a vehicle that can be modified for different vision. And the baseline design has been finalized now, with detailed design is nearly complete, with key interfaces fixed and manufacturing methods as well. And materials defined is the last iteration of individual components to be performed over the next week or 2 to ensure good manufacturability and integration. For some dimensions are shown on the slide. On the outside, the nose cone is 260 millimeters, the upper airframe is 522 millimeters, the avionics section on the outside is 100 millimeters, and the lower airframe, nearly a meter, it's 188 millimeters long, resulting in the overall length of 1.87 meters. The outer diameter is 104.4 millimeters long, to ensure as low form drag as possible. Some of the key parameters are presented on the left as well, with the max speed, as mentioned, not exceeding Mach 1. Also, the launch legs are positioned on either side of the center of gravity, on the same diameter and without obstructions, spaced nearly a meter apart. The bottom launch leg is designed by the team and integrated into the fin can, while the upper one is an aluminium commercial off-the-shelf aluminium rail button attached to the body tube. On the next slide, we can see the rocket top-level assembly. The lower section includes the motor assembly and the main parachute, and is connected to the removable avionics bay with shear pins. The avionics sections houses all of the rocket power systems, telemetry, and communication. It is rigidly connected to the upper airframe with screws. The upper rocket section accommodates the CANSAT payload and then the drogue parachute, and is connected to the nose cone with shear pins. All tubular connections have an at least 1 diameter long overlap region. So, as mentioned before, at the apogee, the upper section, charge at the upper section, just above the avionics, and triggered by the avionics circuit, will shear the pins between the nose cone and the upper section, releasing the drogue parachute and the payload. And then at 200 meters, the lower ejection charge just below the avionics will separate the lower airframe and the avionics sections, which will go into the detail further in the presentation. The key component to mention, as mentioned before, that the body tube is made from glass fiber in partnership with Collins Aerospace to make sure we can achieve high tolerances and obtain a high-performing product to meet our requirements. The main advantage of the body tube is its transparency, which will be a major improvement from last year's to ensure the transmission signal is as good as possible, but also several other advantages like high cooling rate, potentially lower weight as well. The design also features a number of aluminium CNC machine bulkheads and a couple of 3D printed components, as will be explained before, mainly the fin can and the nose and some of the support structures for the internal avionics. On the next slide, we can see in a bit more detail the motor section. So the selected Pro 75 motor is centered and retained at the bottom of the rocket. The thrust is transferred directly from the thrust string via the thrust bulkhead into the body tube directly in compression, and the motor mount is removable, so it can be quickly integrated prior to the launch. Also, we can see the integrated launch legs on the fin can as well, on the left side of the slide. On the next slide, we can see the upper section of the motor with where the motor is centered, and an eye bolt will be directly screwed into the motor forward retention thread, which will massively help with the shock loads. So the shock loads for the rocket has been considered in detail to ensure no failure occurs during the parachute deployment. The largest shock load will be experienced during the main parachute ejection, and from that point in time, profiles for descent velocities have been produced, and also, as will be shown later, stiffness characteristics of the parachute harness has been tested, and this allowed the team to estimate a range of magnitude for deployment shock loads based on the energy balance and to design the structure to withstand those shock loads. The load experienced by the lower airframe section will be largest because the landing mass is heavier, and therefore the shock loads will be transferred through the eyeball directly to the motor casing, which will then leave the motor mount and the tube in compression. On the next slide, there is a closer look at the avionics section, which is an individual section which can be integrated prior to launch, and is close to 300 millimeter long. The thrust force is directly transferred in compression on the inside using a machine step of the tube and the bulkheads on each side of the avionics to ensure no failure or damage is possible in flight due to thrust. The overlap region, as mentioned before, is at least 100 millimeters long. The tube, since it has been made from glass fiber to ensure good transmission throughout. So we expect to achieve high power transmission signal for at least 3 kilometers, which the test of that is ongoing at the moment. On the next slide, finally, we have a closer look at the dedicated payload section, which will house the team-built CANSAT. As again, the thrust is transferred through the avionics to the upper tube and then to the nose cone. As seen, since the overall body tube is made from glass fiber, the signal from the payload in communication with the ground station is also expected to be good. The payload CANSAT, the inner structure of the tube, just below the CANSAT's features several components, as will be described later in more detail, to ensure when the nose cone separates, we can ensure the CANSAT and the drop parachute can be safely deployed. without getting stuck in the tube. We'll now have a closer look at the individual components of the tube in more detail.
So the solar panels are a technology demonstration and are connected to the payload via magnetic connectors. There will be a current sensor present that will monitor the output current of the solar panels. Using the data collected, we should be able to determine whether the solar panels are able to adequately charge the power source when the rocket is required to be on the stand for longer time periods.
The motor mount is mounted to the bottom of the airframe by clamping the motor lip between the thrust bulkhead and retention ring. A forward motor retainer is also located at the top of the motor to avoid unwanted lateral motor movement. It is mounted to the airframe using 4 M3 screws. The forward motor retention uses 2 external and 1 internally mounted O-rings to ease assembly, manufacture, and to protect the parachute from any potential hot gases. The internal O-ring interfaces with the motor casing's shoulder, securing it in place. The lower half of the airframe's parachute is connected to the motor via an eye-bolt screwed into the top of the motor. The motor mount is split into 4 components: the thrust bulkhead, coupler, retention ring, and ballast holder. The steel thrust bulkhead is attached to the airframe via 8 M3 nuts and bolts, which pass through the 3D printed nylon 12 coupler, fin can, airframe, and finally into the bulkhead, as seen in the section view. The motor transfers its thrust directly into the bulkhead, with the bulkhead butted against the bottom of the airframe. To avoid the motor from falling out, a steel retaining ring is attached to the bottom of the assembly using 4 M3 screws through the coupler into the bottom of the thrust bulkhead. Since the target weight of 1.6 kilograms is required to keep the stability within the required margins, a ballast holder is essential. It has been chosen to attach ballast to the thrust bulkheads using 4 threaded rods. The steel rings of known mass are slotted into these rods and secured using washers and bolts. Depending on launch day requirements, mass can be added or removed to achieve the required flight characteristics. Adjusting the ballast steel ring thickness alters its weight, and thereby multiple thin rings can be manufactured to achieve small incremental weight changes.
The fins will be mounted to the airframe through a can that has a 2.5mm thickness that will wrap around the outside. Mounted through 16 M3 screws total, with 8 at the base and 8 at the top. The bottom screws, as previously mentioned, will connect through the airframe to the motor mount, and the top screws will only mount to the airframe. The fins themselves have a root length of 120mm, a height of 93.5mm, and a tip length of 77mm with a base thickness of 5mm. The cross section of the fins is a NACA 4 series aerofoil with a thickness to chord ratio of 4.2%. The fins will be manufactured by the Additive Manufacturing Center of Excellence, or AMCO, by using their SLA printers, and they will be using an in-house polyacrylate resin that they will develop to match our performance requirements that we provide to them. The fin can has been split into 2 separate sections, and this is because the SLA printer that AMCO have available for us to use has a limited print volume that is unable to print the fin can as a single piece. Therefore, it's been split down the middle so it can fit inside the 3D printer. A launch rail has been integrated into the fin can, which has been split into 3 sections in order to introduce redundancy during launch. And a blended structure has been introduced to allow for the fin can and the rear motor mount to meet seamlessly without physical connection to improve the aerodynamic efficiency of the external structure and to control the airflow to minimize turbulence and drag.
The avionics bay serves as the anchor for the rocket. It is the center at which both the main and drogue parachute attaches to, as well as houses all of the critical electrical components that govern flight control. The aviation bay has been designed with high tolerances in order to allow the upper and lower airframe to slide smoothly over the tube and mate at the lips located at the center. It is then attached to the upper and lower bulkhead via 8 M3 steel screws that circle all around the rocket. Since the lower airframe separates during main parachute ejection, those screws are fastened with M3 shear pins instead. The bulkhead aligns nicely with the inner diameter of the aviation tube and rests on the top of either end. These bulkheads are held in compression by 3 M3 steel rods that travel throughout the aviation bay. These steel rods serve to alleviate the extreme forces faced during recovery off of the electronic boards, making sure to keep them nice and safe. The upper and lower bulkhead is also where the charge wells will reside, which will then be ejected at specific timing, separating the rocket and launching recovery parachute. Along with 3 vent holes situated around the avionics, there are a total of 4 cameras, one on each end to capture payload ejection and main parachute ejection, as well as 2 on the side with one facing the horizon, as well as another downward facing to capture initial launch. Along with the camera cover, all of the internal mounts will be 3D printed by our friends at AMCO.
The vehicle electrical systems will be powered from a 3.7 LiPo and a 7.4 Li-on battery. The lower voltage cell will power the MAB sensors and systems, with the higher voltage powering the egg timer proton and the camera board. From the power budget for 3 hours of runtime, you can see with a safety factor of 2, there is a 1.4 amp hours of power is required for the lower voltage. So a 1.8 amp hour battery is being used, and at least 1.7 amp hours is required for the higher voltage. So a 2.8 amp hour is being used. The graph shows a lookup table comparing battery voltage to percentage charge, calculated by draining the battery with a fixed load and periodically measuring the battery voltage, taking the time as the percentage and transposing the results to get the battery voltage compared to the expected percent charge of the battery. The egg timer proton can output its own sensor data, and so this will be read by the main avionics board, so it can be transmitted for analysis alongside the main avionics board sensor readings for more accurate analysis of data. The on-off switch will be a screw switch accessed through one of the pressure equalizing holes and will apply power to the whole system. The 7.4 volt battery will be completely disconnected from the egg timer proton pyro channels until after the remove before launch tab is pulled in the setup process, meaning the pyro channels cannot accidentally deploy.
The payload deployment system is contained within the upper section of the rocket above the avionics bay. Thrust loads are transferred through the airframe from bottom upwards, so like left to right on the screen. They're then transferred to the O-ring through the piston head and then to the payload. The nose cone secures the payload, however, the load is still transferred to it, like via the airframe. So like to outline the deployment system, it's comprised of a 65mm deep pressure chamber that contains the pyrotechnic charges. At the top of the chamber sits the O-ring, secured with screws around the airframe. This retains the piston heads, which holds the payload, but also allows gases from the pyrotechnics to expand up the tube. The piston head slots into the O-ring and has a hole through the middle to allow the drogue parachute cord to be threaded through, which is sealed afterwards to retain pressure. The cord itself is a 1/2 inch diameter and is attached to an eye bolt on top of the avionics bay with slack to allow extension of the piston, then through the piston heads, up past the payload and attach the drogue chute before attaching to an eye bolt in the nose cone. The drogue chute is packed into the nose cone, which is pulled out on deployment as shown in the next slide. Deployment occurs first with the firing of the pyrocharges, which will create an expected 1 kilonewton of force on the bottom of the piston head. The piston head pushes on the payload, which transfers the force to the nose cone, causing the shear pins holding the nose cone to break. At the same time, the electronic connector releases, disconnecting the solar panels in the exterior of the airframe. The piston and payload then extend up and out the inside of the upper airframe, pushing the nose cone off and separating the payload from the vehicle. The drogue chute is then pulled from the inside of the nose cone before inflating. All components except from the payload remain attached by the parachute cord.
Once the rocket has reached 200 meters, the main parachute will deploy. Charge wells at the bottom of the avionics bay will ignite, breaking the shear pins and separate the lower half of the rocket into 2 parts. This will release the main parachute that attaches to the avionics bay and lower airframe, thus slowing down descent considerably, hopefully guiding our rocket towards a safe landing.
Here is the mass breakdown of the launch vehicle. The total mass is 11.3 kilograms, and the largest portions of the mass are, in descending order, the motor without the casing, followed by the airframe tubes, which are both just over 2 kilograms, then the motor casing at 1.7 kilograms, and the ballast at 1.6 kilograms, which is significantly reduced from PDR.
So now we'll quickly go over the propulsion and flight analysis statement.
OpenRocket has continued to be used to analyze the stability parameters of the vehicle throughout its mission profile, and it shows the stability remains very similar to the preliminary design review, with the vehicle exhibiting an initial stability of 1.5, and not exceeding 2.5 throughout the course of flight. The vehicle will also remain subsonic throughout the flight, reaching a maximum velocity of 273 meters per second or 0.81 Mach. The ratio of the length of the rocket to the diameter of the rocket is now 18.0, and due to the length of the rocket and the weight of the motor, the center of gravity of the vehicle shifts a large distance as the motor burns in the initial stages of flight, causing a large variation in the stability, and as such a large ballast bay close to the bottom of the vehicle was introduced to bring the center of gravity down further throughout flight. Finite element analysis of the longitudinal load case of the fins has been carried out by applying a load case of 25 newtons to the tips of each fin, as per the load case of 2 times the fin mass multiplied by the maximum acceleration experienced by the vehicle during flight. And this results in a minimum factor of safety of 49 and a maximum longitudinal displacement of 0.0608 millimeters. The lateral loading is still yet to be validated using FEA, and test parts are in the process of being printed in order to allow for physical testing. And this analysis that you see here was done with both halves of the fin can simultaneously, and the results compared to FEA done prior to splitting the fin can shows that the structure of this can has not been affected or weakened by this split. The nose cone consists of a COTS aluminium nose cone tip mounted on top of a polymer 3D printed nose cone base using an M6 threaded eye bolt. The base is hollow with a wall thickness of 2 millimeters and also contains 6 stiffeners inside the cone section in order to increase the rigidity under load. The maximum acceleration experienced by the rocket during flight is 65.1 meters per second squared. However, the load case applied to the nose cone in this simulation here was 100 meters per second squared in order to introduce a further factor of safety on the design. And the resultant minimum factor of safety of this load case was 229, resulting in a maximum displacement of 0.00467 newtons. We are currently working on introducing further load cases in the form of the pressure experienced during flight and the deployment loads caused by the pyrotechnic charges.
The launch day conditions are expected to be similar to previous years. Last year's launch was on the verge of being too windy, although this is rare. Wind and temperature variations can affect the flight profile, so this will be simulated on the day. The apogee range is between 2,885 and 2,995 meters, based on variations in the temperature and pressure, with higher temperature and lower pressure being preferred, as this gives us an apogee closer to 3 kilometers. The wind rose on the top right shows that high-speed winds usually blow from west to east, though lower speed winds typically blow northwest, which is out to sea. This is part of why keeping the drift from the launch pad to a minimum is so critical. The launch vehicle and payload must not drift out to sea.
So the motor has been ordered by Malcolm Rockets, and we're planning on sending the grains to Mach-23 as well as the motor casing to University of Nottingham soon. The loading for UROC is greater than Mach-23, so we're conducting tests with UROC loads, and the loads expected up the length of the airframe have been showed in the previous slides and also will be in appendix. It's planned to do compression tests in the next couple of weeks, where we will load the test piece that's arrived at 1.5 kilonewtons. Both deployment events use black powder ignited by the egg timer proton. Additionally, we may fly a redundant egg quark computer with parallel charges. The drogue charge is estimated at 0.32 grams, and in the 99.6 millimeter tube, which is 65 millimeter long, that will produce a load of 1,000 newtons. This will shear 2 M2 shear pins. However, as we're using piston deployment, the force reduces as the piston moves throughout the length of the tube. The length of the nose cone lip is 100 millimeters, so once the piston is extended, or the chamber is extended to 165 millimeters total, the nose will deploy, and at this point the load experience is still 400 newtons, so we're confident this will be able to eject the payload. This deployment event will release a 12-inch drogue parachute, which will slow the descent rate to under 39 meters per second. The main charge, which will deploy below 200 meters, will produce an 1,000 newton force to shear 4 shear pins, which requires a 1.6 gram charge. We bought some charge canisters from Black Cat Rocketry, but they're quite large, and we're not actually sure how they work 100%, so we're considering 3D printing or milling our own. And this deployment event will deploy a 96-inch main, which will bring the descent to roughly 5 meters per second. Additionally, as mentioned, we're calculating shock loads for this case. There are 2 parachute harnesses, one for the main and drogue. one for the main and one for the drogue. The drogue parachute is attached to the middle of the 5-meter tether between an eye bolt on the top of the avionics bay and an eye bolt used to attach our nose cone tip. Additionally, this runs through the piston and holds that from falling freely. The main chute is then attached to the middle of a 10-meter tether, and that's attached to the eye bolt screwed into the motor casing, as well as an eye bolt in the bottom of the avionics bay. These descent rates can be used for drift calculations, where if the apogee occurs exactly over the launch point, the drift could be 1,575 meters in 15 meters per second wind. However, the point of the apogee over the launch site is a function of the wind speed and the launch angle. Due to this, a final flight simulation will be conducted on the day to determine the best angle to launch to reach 3 kilometers while minimizing drift. Under typical conditions of 5 meters per second with a 5-degree launch, we only drift about 200 meters from the launch. 500 meters from the launch site, with the main deploying roughly a few hundred meters away. Higher winds do lead to greater drift, but even at the upper limit of 15 meters per second, the drift is only 1,100 meters.
The ground station itself consists of 4 active components: the microcontroller, 2 transceivers, and an LCD. The microcontroller is a Raspberry Pi Pico. This will communicate and control both transceivers as well as the LCD. It has built-in USB communication within the RP2040 chip rather than an external UART to USB converter for easy communication with external app and ease of programming. This means there are fewer components, reducing the risk of component failure. The transceivers are from RF Solutions. The Zeta module is used for the 2.4 GHz payload communication and the Lambda 62 module for the 868 MHz main vehicle. This module doesn't automatically set the duty cycle to within frequency band guidelines, so the 868 MHz duty cycle will be kept below 1% within the program software. These will connect to the Pico via its 2 SPI channels. The LCD will use the remaining data pins to communicate with the microcontroller. The ground station will be inside a waterproof container to be impervious to the elements, with a basic LCD display to show the basic required recovery information, such as GPS coordinates for both payload and the vehicle, to allow for easy recovery in case weather prevents the full ground station app being used. The ground station app is built in Electron.js and uses web APIs to access the output serial USB data from the main ground station. This plots the data in the graph and shows a live 3D model of the current orientation of the vehicle. The basic layout of this app can be seen here. Some of the important flight data points that will be displayed are the velocity, the orientation in relation to the Earth's surface, the GNSS position, the atmospheric pressure from which altitude can be determined, and any acceleration forces the vehicle is experiencing. The Raspberry Pi Pico uses an RP2040 chip. This is very little internal memory, and so there is an external flash chip on board. This flash chip is mainly used for program storage, but is large enough to store as much more data than the small amount being taken by most programs. Since the program is always stored in the beginning few memory addresses, the addresses at the end of the flash chip are left free. These locations are utilized within the ground station and main vehicle to store flight data. While an EEPROM could be used, this would be an additional part to go wrong. An EEPROM would also provide a greater number of read-write cycles, but for the purposes of this application, the flash chip provides ample lifetime for the storage of many flights worth of data. The app stores flight data received through the USB interface for access to flight data without the need to extract the data post-flight from the main ground station or the vehicle. So in total, the data will be stored in 3 locations. Once on board the vehicle, this is expected to be the most reliable. The ground station itself will store all the transmitted data as a backup in case of failure and recovery, and once within the app for analysis during flight. The ground station will run at 5 volts, being powered by either the application computer or an external power bank. Like the main vehicle, 180 minutes of runtime and a safety factor of 2 was used for the calculations, concluding that approximately 3 amp hour battery will power the device for up to 3 hours.
The structure of the payload consists of a phenolic coupling tube, which contains a central aluminium bulkhead separating internal components and is compressed by an upper-lower bulkhead with 2 steel supporting rods running the length of the structure. 4 spring hinges are screwed onto the upper bulkhead and will connect to the flaps of the payload, and fabric will be attached between the flaps using screws and epoxy to increase the surface area. An aluminium parachute housing is also integrated as part of the upper bulkhead, giving room for a parachute to be attached to the eye bolt and strategically stored for deployment. A vertical rectangular slider for mounting electronics will be slid onto both the supporting rods to allow for better load support as the load goes through the electronics bay. The slider is made from PVC polymer, which is a strong material and will decrease the chance of any deformation of the electronics bay during launch and landing. Having a slider also allows for improved accessibility of the electronic components compared to a stacked structure where only one layer of electronics would be accessible at a time. By modeling all electronic components to size and adding to the assembly, it has been confirmed that they all fit on the 110mm by 66mm slider. One large change since the PDR is the inclusion of a parachute to the payload design. A parachute housing and eye bolt were already included in the design for the purpose of adding a streamer if needed. The addition of springs between the sliders and bulkhead is also a change made since the PDR. These have the purpose of ensuring less damage to the electric structures within the payload during landing, as the springs will absorb some of the shock acting on the internal structures. Another change is the hollowing out of the upper bulkhead. This is to allow the center of gravity of the payload to be close to the bottom of the structure, giving more stability during descent.
Descent control for the payload consists of a small parachute deployed at peak altitude, as well as deployable flaps. The stowed configuration will be flaps down with the parachute packed into the parachute housing in the top bulkhead. Once deployed from the rocket airframe, the payload parachute will open up as the payload falls, then at 100 to 200 meters above the ground, the flaps will be deployed. A COTS flight computer will be used to determine when these deploy, sending a signal to melt fishing wire, which will release the flaps. As discussed, these will flap up via 4 spring hinges mounted on the upper bulkhead. A second set of fishing wire will also be attached to the flaps to prevent over-rotation, ensuring the flaps deploy perpendicular to the CANSAT body. Once the flaps are up, the fully deployed configuration will have been reached.
The first stage of descent is initiated once the parachute has been deployed. The parachute will have a diameter of 12 inches, giving a total area of roughly 0.15 meters squared and a drag coefficient of 1.11, creating enough drag force and decreasing velocity to a level safe enough to initiate the second stage of descent. Assuming there will be a maximum of 5 meters per second of crosswind, and that the deployment of the parachute goes as planned, the payload will reach a descent velocity of roughly 15 meters per second at the end of this stage. The second stage of descent begins when the payload has reached an altitude of 100 to 200 meters above the ground, which is when the flaps are deployed. Each flap has a frontal area of roughly 0.01 meters squared and a thickness of 1.5 millimeters. After calculating a Reynolds number of 3.9 times 10 to the 5 and a drag coefficient of 1.05, the combination of drag force of the parachute and the deployment of these flaps will further reduce descent velocity from 15 meters per second to 7 meters per second, which is a velocity safe enough for landing.
So the battery should last for about 3 hours. The solar panels will be connected to the battery via magnetic connectors and will be able to charge the battery on the stand. This will be more of a technology demonstration, and so current and voltage sensors will be connected to the solar panels to determine if this is a viable method. The switch for the power source shall be easily accessible via an external switch. In most situations, the solar panel will generate enough power from the available solar irradiance to power the electrical systems and keep the batteries charged right up to the moment of deployment. From there, the battery will be relied on to power all systems until recovery. However, the battery itself is rated to power systems for the duration of the mission in the event of the solar panels failing to provide any power while on the launch stand. As the COTS computer is powered separately due to its significant power draw, the total power draw is calculated as 783 milliwatts, and since a 3.7 volt battery is being used, this requires a 211 milliamp 3.7 volt current draw. Adding a 3-hour runtime and a safety factor of 2, a 1.3 amp hour battery is required, and so a 1.8 amp hour LiPo battery was chosen with a nominal current draw of 340 milliamps. In the unlikely event the solar panels cannot adequately charge the battery, the choice of battery ensures that the payload can meet mission requirements. This chemistry was used due to the readily available chargers for this battery type, especially with single cell when no balancing load is required.
Next is our testing plan. So we have an extensive testing document detailing all the tests needed to verify the project's requirements. This is showing that we're 19% through all testing currently, and tests are being completed against specific requirements to ensure compliance. Shown in the video on the right is the tension test of bungee cords completed earlier this week. The most critical test is the planned full flight test at Midlands Rocketry Club, in May, which is yet to be confirmed. And completed tests will be highlighted in green, progress in yellow, and not started in red. FEA has been performed on the fin can to meet guidelines on lateral deflection and withstanding longitudinal load. Longitudinal testing has passed, but lateral loading has not yet been completed. This FEA must then be verified with experimental tests, which are shown on the next slide, of which there are component tests and subsystem tests. Lateral and longitudinal loading will be tested first just on a clamped fin can and adding weights until the required load case has been achieved. This test will be repeated with the fin can mounted on the lower airframe tube, and depending on the number of fin cans we can manufacture, we will test this to destruction. Deployment tests consist of black powder deployment and a test flight, which are yet to be completed. A stiffness test of bungee cords has been completed, as shown earlier, which determined that the bungee cords make negligible impact and will not be used. Many avionics tests have been ongoing, although the final testing, once the system is completed, will consist of RF transmission testing to ensure telemetry can be received during flight. Testing of the payload avionics consists of testing the code runs correctly on the microcontroller, followed by testing of individual components, then stripboard tests of the entire payload avionics system. Payload structure testing will include RF transmission tests similar to the launch vehicle's avionics, as well as FEA of the CANSAT structure and spring hinges. Once all other tests have been completed, a drop test of the CANSAT with flaps will be completed, verifying all aspects of the subsystem function as intended. Now moving on to the safety of the launch vehicle. Violin has been designed to the competition guidelines. Requirements not covered completely by the design itself, for example the aspect ratio, will be verified with tests. Each test has been planned to verify one or more requirements from our document, which includes the competition's and the team's requirements for the vehicle. Many tests will verify multiple requirements at once. As shown before, there are many tests planned. Some requirements will be verified with computational techniques, for example, CFD, FEA, and open rocket flight simulations. For instance, our open rocket flight simulations will be validated by the test launch, showing our open rocket model is accurate. Here is the table of risks to the project. Risks that have changed since PDR have been highlighted in bold. One of the most significant risks to the project is failure of the payload flaps. This has a high impact to the project as it would cause the CANSAT to descend at unsafe speeds. This is mitigated by the flaps being designed to withstand at least 2 times the maximum expected load during flight without failure, and this will be tested thoroughly. Another potential issue is failing to meet stability requirements. Our current design meets the criteria, although design changes could lead to minor overstability. The design includes a ballast bay to tune this based on our mass breakdown, but this presents a trade-off against our target apogee. Electronics disconnecting during flight is another concern, although connections within the avionics will be made to withstand expected forces with a safety factor of 2, and due diligence is being used while manufacturing and assembling avionics. Our main risk mitigation strategy is that we are testing early to prevent unforeseen problems later in the project.
And I'll briefly cover some of the project planning that's ongoing. So the entry fee and accommodation, as well as the flight insurance, should now be paid, although it's always hard to tell with our procurement team. Additionally, some of the components have begun procurement with a focus on electronics to allow some practical work to take place. The budget has grown by £525 since the PDR, and at that rate of growth, the total budget could reach around 6,180, but this is still significantly within the total budget, leaving almost 9k for UROC associated costs. We are currently still on the schedule presented at the PDR. However, due to the previously mentioned procurement delays, assembly may be slightly delayed. And with the Easter holidays coming up, as well as exams, it's likely that a lot of the work will have to be completed after exams when there are no other distractions. With that noted, we can track the work packages here. Currently, we're at about 50% completion, which is ideally behind where we'd like to be, but a significant contributor to this are tasks that are 95% complete, but we don't yet want to make them complete yet, just in case we need to make any final changes. Ideally, we'd opt for the S-curve of workload, but as is often the case with student projects, we are steering towards the student curve, which isn't the worst thing, as it's a tried and true method of finishing the project, and the final 4 weeks before the launch event, again, are undisturbed by university work, so it's a good time to get a lot of the work done. And I think we have a good backbone, or like good pillars to stand on already. So to conclude, we presented our detailed design of Violin, as well as the plans going forward, including how we cover the requirements. We're happy with the progress, and we're very excited to come to the launch event in June. And we've started work on testing, manufacturing, and assembly as early as possible to try and prevent delays. Electrical integrations behind were ideal, but due to procurement issues, and this has been sorted now, so they should be on the way. Yeah, we'd like to finally thank Chantal Capoletti, our project supervisor, for supporting us throughout the project. Jez Turner, who's one of the most enthusiastic guys I've met, who is always offering support where possible. Miriam, who has encouraged us to apply for grant funding. Steve Greedy, who's supporting Daniel Hutton's electrical project on the avionics. The Not Space group, who constantly solve random problems we may encounter in a very timely manner. James Rouse, who's helping us set up compression tests, alongside Richard Homer, who is also setting up compression tests. Humberto Medina, who is helping us work with wind tunnels. RS Grassroots, who have provided us with funding, as well as skills workshops, as well as Andrew Hallam and Tom Haskins, who are the technicians that we are constantly working with to provide various different capabilities. AMCO, who have started 3D printing parts for us, as well as Collins Aerospace, who has been manufacturing the airframe. Thank you for your time. Please email any questions to this email.